All right, welcome in, guys. Last time we had a quiz. I haven't quite got through all of those just yet. So I'm thinking next time I'll have those ready to hand back to you. And then if you want to go over it, we'll say like after that session, we'll go over the quiz. But for today, we are starting a new chapter. We're starting topic 6, momentum, impulse, and collision. All right, this is one of the more fun chapters I think of because it's very direct. As soon as you get the concept, that's the whole thing for the whole chapter. So we start out talking about linear momentum. What is linear momentum? Well, in general, I could say that all objects with mass have momentum. When we started out the semester, I was saying something like all objects with mass have inertia. And inertia is just any sort of physical object, this table, those chairs. Inertia is a resistance to change. That was related to Newton's first law. If I have this chair, I'm going to use these chairs a lot today. If I have this chair, Newton's first law said an object at rest tends to stay at rest, an object in motion tends to stay in motion. That's why it keeps going for a while, until friction slows it down and stops it. But momentum is a little bit different. You think of momentum as mass in motion. So think of it as how much force you need, or think of how it's like a quantity that says how the mass relates to how fast it's moving. Let's see. In general, the equation for momentum is a lowercase p equals mass times velocity. Now, something you should say about this equation is you know velocity is a vector. I should put a vector sign above velocity. And that also means that momentum is a vector. So the direction of momentum is important. And so if we have this equation, and let me put the units, it's very straightforward. We have mass, that is the SI unit of kilograms. The SI unit of velocity is meters per second. And so the unit of momentum is just kilograms times meters per second. Or you might see like something crazy like a Newton per second or something like that. So that's, if I add, one more something over a second, we get a Newton. But typically we could just write the units like this. So you see this chair right now, as it just sits here, it has mass, but it's not moving. So it has no momentum, 0. And for you guys, this is left. It has negative momentum and positive momentum. Go to a little quick sidebar. I used to drive a car like this. This was my first car. I drove for about 12 years. what I learned to drive in. Not this exact one. This isn't. I didn't take this picture. I found this on the internet. It was real cool that it had a seatbelt that just like auto, like it just rolled up the track over your shoulder. It was something that I don't think it could go 60 miles an hour. I don't think I ever took it on the freeway. I was afraid to. So let's say we have this car right here, is very small, that is moving at a velocity of, I'm going to use meters per second because then they'll make our problems easy. 50 meters per second. I didn't look up beforehand what that is in miles per hour. We're just going to say 50 meters per second for right now. So something, a comfortable speed probably. So let's find the momentum of this car. Is 1,300 times 50. See that? I haven't done this beforehand, so let me. Okay, so we get 65,000 kilograms times meters per second squared. Just meters per second. Awesome. That's a vector, that's a vector. We have our answer. Now, let's say we have a different object. This truck, it's moving at the same speed. This truck is much, 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 much more massive. I can immediately, you see how this concept's a little straightforward. You just immediately see it's going to have more momentum, drastically more momentum. So, 36,000 times 50. Let's do this one. All right. 1,800,000 kilograms per meters. Kilograms times meters per second. Awesome. So as things get more massive, they get more momentum. And like I'm sort of relating it to inertia, it's sort of, imagine as how hard it is for this object to stop. So less momentum, we have these two things at a stoplight. Green light flashes, and the one with less mass, it's able to get up to speed quicker. It has a smaller inertia, and it might go at the same speed, but eventually, if the truck goes that equal speed, it will develop much, much more momentum than the smaller car. And we can go to the very drastic example of a train. Now a train engine has to pull, I looked it up and I converted it. This is roughly about a fully loaded freight train right here. And let's find how much momentum, let's see how easy it is for this thing to stop. So we're figuring out that greater momentum means that it's harder to stop. So let's see what kind of momentum we have here. So that's 4,500,000 kilograms. Let's just go like this. No, I'll write the full thing right now. And it's not moving that fast. It's moving the same speed, same velocity. 4,500,000. Okay, I'm not going to write all of that, so I'm going to go 8. And what this is saying, let me sort of say it. So it's 225 million kilograms times meters per second. So this is, I hear like advertisements on the radio that just are advertising, don't walk on train tracks. This is why. Trains have a lot of mass, therefore they have a lot of momentum, even when they're going very slow. It means it takes a lot of energy, a lot of, it's a lot of force and power to try to stop this, to make it come to a rest. Whereas not so much for, a small car, kind of like what I had. All right. So we've talked about momentum. It's a property of an object that moves. Let's talk about impulse. This is going to be sort of a thing where we know that something that's moving will have a momentum, but it has to have originated from something. This chair isn't moving as it is right now, but I might apply some force to get it to start moving. So that brief interaction of me pushing it, that is what we're calling impulse. So that small little push for that tiny amount of time, that is what impulse is. So an impulse is the change of an object's momentum. I should have had a apostrophe there. So impulse is change in momentum. So that's one formula we could, or that's one form we could write this in. What else can we say about impulse? Well, kind of like what I just said. I had to force this thing to get it to start moving. A lot of things require a force to get them to do something. So a small push here. And what kind of examples can I imagine? Like a baseball. Like when someone pitches a baseball to the batter, the ball only strikes the bat for a fraction of a second. We're going to call that an impulse. So there's a force over a small amount of time. So with this force, we're going to call, or we're going to create what I'll call the momentum, or the impulse momentum theorem. That's what it says in your book. And it's basically just a way for you to see what kind of forces relate to, a momentum. So I have a force. How do I get momentum? Sort of an equation relating the two. It looks like this. So impulse is just, how much force you're applying just over a specific amount of time. It looks kind of like work. It's not work. This is just force for a specific moment of time. And that is equal to change in momentum. And let me write out what this delta P is meaning. So that's final momentum minus initial momentum. So it equals P final minus P initial. And then let me fill that out even more. So it's just that final velocity minus the initial velocity. Oh, sorry. There we go. Yeah.
What did the F represent again?
F, that's just a force. That's me applying some force for a small amount of time. This could be me speeding something up or slowing it down, just changing its velocity. All right, and I should technically, right here for the M, MV final, I should put like M final minus M initial as well. But typically, for big everyday objects, me pushing this chair, all day, the chair isn't losing mass as I give it a push. Its mass when it started is the same as the mass when it starts rolling. But some things, maybe like a car, or later in the chapter, it talks about rockets, rocket propulsion. So right at the beginning, now we're going to imagine there's a rocket strapped to the chair. Right at the beginning, we got to measure its velocity now and its mass now. But a lot of mass is coming out as the rocket fuel. So once the rocket starts going for a while, a lot of the fuel is spent. And then some later time, it has a completely different mass. And it's moving at a different velocity. So I'm going to put it up here technically. Final and initial, just like that. I don't know if I'll give you guys a rocket equation or anything on the homework. That's pretty much impulse. Let's do a quick little example of an impulse problem. So this is talking about a golf ball being struck by a golf club. So we have a 200 gram or 0.2 kilogram golf ball. It's initially at rest and then struck with a golf club with a force of 50 newtons. The moment of impact, so it's just a golf swing. Is only a very small amount of time. So let's find the impulse acting on the golf ball, and then let's find what's the velocity of the golf ball after we sort of hit it with this amount of force. So first off, I'm just going to write what I know. That's just the equations I've written down before. Okay, pretty easy. I already have everything I need for the impulse. That is awesome. 50 newtons and 5 seconds. I didn't look up if that was an accurate time. Maybe it's slow, I don't know. So this is going to be like 2.5 or something. 0.05. 2.5. And here's the case. I didn't give you guys the units for impulse on the previous slide. So how can I figure out the units? I look at the equation and I look at what units are in that top row. So it's force times time. So unit of force is a newton. Unit of time is seconds. So I can just say newtons times seconds. And that is acceptable. All right. What is the velocity of a golf ball right after it is hit? Okay. Let me write just a bit more of what I've just written on the other slide. Change in momentum. Okay, let's write the full thing. Mass final. Okay. So final momentum minus the initial momentum. I should put arrows above these. I'm gonna forget. Okay. So what is the initial velocity of the golf ball? 0. It says at the beginning, it's not explicitly said that this equals 0. It said the ball is at rest. So that means it starts at 0. And so that means this whole term, the whole term with m sub I and v sub I goes to 0. All right. All right, and we've already found the impulse for this problem. We found it up there. It's at the top right. And we already know the mass of the ball. So this is a very breezy problem. So 5 all right. We get let me write this over and over. Okay. Someone get there before I did. Let's see. .5 meters per second. So, not incredibly fast. I think I probably just assumed a wrong value. That seems a little slow for a golf ball. It's going to make it go a lot faster than that, I think. Although at 12 meters, that's probably me to the back wall in 1 second. So it's fast. I think a golf ball goes a little faster when you strike it. Yeah. But that's pretty much plain impulse problem that we're going to have for this chapter. All of the other types of problems are going to be revolving around momentum and the conservation of momentum. So when we have a system, let me not use the chair for this. When you have a system and there's no external forces acting on anything inside of the system, then we can always say that the amount of momentum will remain constant for that system. Right. get to this in a minute. So when we have a system that is made of, one or two things, we're only going to look at those one or two things, and we're going to call that our system. That's our perfect little bubble. And if no forces are interacting with it, there's no friction or someone else comes in and disturbs it, then we can say all of the momentum in our system is the same amount. It just might, switch from one thing to the other. So while we're looking at our system, momentum can transfer from one thing to another. And we can figure out how just by adding up the total before an interaction and the total momentum after an interaction. I'm saying interaction because in a bit we're going to go over collisions. Slightly different than an interaction. So, in general, I'm going to write the general version of this, in equation form, is, however many things we have, I'm just going to say momentum initial is equal to momentum final. These should be vectors. And for, a couple of examples in a lot of your problems, it's typically only going to be two things you got to, keep your mind around. So on this example, I have two cars, and before I get to that, I have two chairs. Let me fill out the rest of this equation first. So let's do it for two objects. So we have momentum of 1 initial plus momentum of 2 initial is equal to momentum of 1 final plus momentum of 2 final. You see, the total amounts will be the same. I'm going to go just one step further, just fleshing it all out. All right. So, the bottom row looks like a mess, but all it's saying is the total momentum before is equal to the total momentum after. So I don't know if this is going to work too well. We'll see. I have two chairs. I need a volunteer to sit in the chair. So what we're going to do is just sort of push off of each other. I'm not going to torture anyone up here. Awesome. All right, cool. So you see right now, we're both in the same chair. We probably have about the same mass, but we're not moving at the moment. So we have no momentum in total. But you turn around for me. So Now, let's say I push off of him. We're both on wheels. And then I apply an impulse, a force, over a small amount of time. And then we do start to move. So us two, we are a system. And we're going to be, moving. But the momentum has to remain the same. I'm going to assume that the floor is frictionless. All of that perfect stuff. So what we're going to do is sort of like grab in the middle. Let's go like palms out. So I'm going to push. You just got to keep your arms straight.
Like this.
So do it like that so it doesn't slip under. All right? Okay. And I'm going to go one way. He's going to go another. And remember that the directions are important. So that even though we are both moving now, the total momentum remains the same because the direction is important. So let's do it again. I'm going to do it like, oh, here. You slide over there. Do it like a good one. All right, ready? So we both go, a similar distance, so we're about the same mass. Let's say one of us is more massive than the other. Someone maybe a bit smaller want to volunteer.
Am I smaller?
You can try. So I went about here. You went about the aisle. Kind of by the green mark here. All right. But you just got to go like that, like up it, so I don't doesn't slip. Okay, we'll do it like practice. Ready? Here we go. So I went less distance. I had a smaller velocity. She went a farther distance. But the total momentum in the system remained the same. And it's all, in this case, it was related to the amount of mass. All right, good job.
It's going to be embarrassing if I have more mass. And then
But I just go through the wall. Yeah. All right, yeah, thank you guys. So we have, that's low-tech example. I have a similar case up here. Maybe before So I have these little gliders. They are about the same mass. And this is an air track. This is like an air hockey table. A lot of tiny little holes in it. And these things will glide. Almost frictionless. Much more than the chairs example. And do it like this. Like this. Let me just do one. Give it a push. And it moves with the same velocity. This is what I was trying to show you guys, is that give it a force, it will keep moving forever until something acts on it. All right? Good. So what's going to happen right here is going to be called a collision. These two things are interacting with one another. Let's go over what type of collision that was. After this example. Awesome. I got ahead of myself. Okay. So this is the case with, the two of us in the chairs. This is just a slightly different example of someone standing on some frictionless ice. Now try to picture the air track example. Like, as soon as just any amount of force happens, you'll start to move. That's frictionless. So, 80-kilogram person is standing out on a frozen lake. and they fire a rifle for some reason, horizontally. Okay? Now, the mass of a bullet, this thing is going to be like tiny. Oh, it's a rifle, so it'll probably be about that, like that big. Right? Not that much mass, but it's going to go incredibly fast. So let's look at the momentum of the system before and after this person fires the gun. So just in general, I'll draw like a block for the person. And there is the bullet. I want to try and make it real simple. And then afterwards, I'll go over here. This is going to go really fast. And we have to figure out from the question, what is the velocity of the person after the bullet is fired? So let's look at momentums. So initial momentum is equal to final momentum. That's our system, this person and this bullet. And nothing's acting on it, so it's going to be the same. Initial equals final. And I should put initial on these. Final. Final. Okay. Now this is a really sort of easy example because what is the initial velocity? Think of us with the chairs. It's the same thing with this example. What's the initial velocity of the person and the bullet? 0. They're both together. That's our system. They're not moving in that first picture. So we have this go to 0, and we have this go to 0. So that whole left side is 0. That makes this incredibly easy to do. So we have 0 equals mass 1, final, mass 2, final. And let's say, I haven't labeled these yet. Let's call the person 1, let's call the bullet 2, just so I can solve for the right one for everyone. So, what's the velocity of the person? So we need to find V1F. So I would subtract over that first term and then divide by M1. And we're going to get something that looks like this. All right, let me put this up here so I have more space. And let's put in the values that we're given. The mass of M2 is the bullet. That's what I said. So we have 0.05 kilograms. We have the velocity, bullets, and we have the mass of the person. And I should careful, I forgot to include, there's a negative sign that should be in front of all this. Oop. Let me, instead of writing a bunch of arrows, do we have like a stick or something? Ah. So right here, when I subtract that over, that's negative. And then I had a negative sign that's left over. That's where this negative sign comes from. Which means this is negative up here, and we have a negative 0.625 meters per second. And the negative in this case is telling us we're moving to the left. All right. So let's say this person is moving to the left just a little bit. 0.625. So fire gun, you're like slide like that far in a second. You're moving actually like kind of quick. Going from a rest to that, you'd probably fall over. All right. So now we're going to look at collisions. That previous example was, two things in a system that were leaving. Now we're going to look at what if two separate things sort of just interact at a midpoint and then maybe continue on their way somewhere. There are two types of collisions that we're going to look out for. One of them is elastic. It's just referred to as an elastic collision. And the other is an inelastic collision. Let's see. So for both of these types of collisions, momentum is going to be conserved. So let me write that out. Momentum is conserved for both of these. But that's where they sort of part ways. They're no longer like each other. An elastic collision, what I like to think about is they used to call like a rubber ball, a bouncy ball. They used to call it like an elastic ball or something like that. It's something that bounces. It's a bouncing collision. Things just bounce off of each other, and they don't interact for that long. So for this bouncing collision, for an elastic collision, the kinetic energy is also conserved. So if one of them means bouncing, the other one we already know, that's when the things stick together in a collision. So think of like if I had maybe like a ball of clay versus a bouncy ball. Elastic collision bounces up, very perfect sort of bouncing off of each other. If I dropped a ball of clay that's inelastic, it just sort of splats on the ground, and it doesn't come back up. So this inelastic collision, I'll say, kinetic energy is not conserved. All right. There we go. So we have this elastic collision right here. So everything just perfectly, this is a somewhat perfectly bounce off of each other. They don't interact for that long, when they're touching. Since it's an elastic collision, the total momentum, before the collision is equal to the momentum after the collision. So let's keep one of them still. And this is before, when this is coming in, and after the collision, after they bump together, the total momentum remains the same. So before and after, momentum can be transferred from one object into the other. Okay. So let me sort of draw a picture of this so you guys can have in your notes. So let's say one of them was at rest and the other comes in with some velocity. Let's just make it both sort of moving a little bit. So this is M2 and it's moving, I don't know, initial, and then since I have colors, I'm going to use them. We had something like this. Right, they were both kind of moving the same. One was maybe moving a little faster. And then they collide. And where are they going to go? Well, M1, V1 final, and M2, V2 final. See, they kind of go like that. So that's sort of a small diagram. And you could do many types of initial setups. Maybe one of them is at rest. Maybe they're moving towards each other. That would only change the sign of the velocity. Positive to the right, negative to the left. And we would just do the same thing we've been doing before. Initial momentum is final momentum. And let me write the full thing out. M1, V1, initial. Okay, so this, one rule, this one line is the momentum being conserved. Now let's express the kinetic energy being conserved. So that just means kinetic energy before the collision is equal to the kinetic energy after the collision. So just total, however many things you have in your system. This is almost a bit too much even with only 2 things. So it looks like this. 1/2 m1 v1 squared initial. Like that. So we can only do this for an elastic collision. Use either momentum or kinetic energy. You say they're equal before and after the collision. We have that tool. But now, maybe the things stick together. Maybe it's not a perfect elastic collision. Maybe, I'll leave it up. Maybe they stick together. So give this one a little push, and then it's going to go as an inelastic collision. They're going to stick together. A little bit. So once they're stuck together, they have this new velocity together, and the momentum is conserved, but the kinetic energy is not. Let me do that one more time. Okay. You're actually going to be doing a lab kind of like that. Let's look at that situation. So we have 2 masses that are going to stick together after the collision. We'll just say one of them is at rest. That's easy. And then, all right, mass 2. It has its own velocity. In this case, it would be 0 if it's not moving. Then we have mass 1 with its own velocity. I should be making these vectors. And then after the collision, they're stuck together. I'm just going to make it a new velocity. I will call it velocity 3. So they're stuck together. And they create this, their velocities add together. So we can see, conservation of momentum always applies. Same thing. M1 V1 initial, M2 V2 initial. This is where things get a little bit different though. It's not V1 final on the other side. It's V3 because they're stuck together. Right? It's the same thing for mass 2. And if I wanted to, I could factor out, that V3 to have it M1 plus M2. Let me just go M1 plus M2 times V3, if I wanted to write it that way. And I can't do those other few steps for kinetic energy because it's not conserved in a inelastic collision. All right, I think is that. See, I only have a couple more things left. The masses stick together. Yeah. Collisions in 2 dimensions. I think we will start next time. Before I end the class, though, I have this really cool, large Newton's cradle up here. And what we have, these are steel ball bearings, and they're going to create an elastic collision. They don't stick together very well. So I can raise one up and let it go. I could also talk about the energy and things like that. But I could give this, I can lift it up, let it have some velocity. And so this one ball right here will have momentum. None of the other ones will. But this whole thing is my system. And I have to say momentum is conserved in the system. So what's going to happen when it strikes this? Well, momentum will transfer all the way through to this one over here. All right. So if this was in a vacuum, the hinges were perfect, this would go on forever. Okay. This is a conservation of energy and momentum, sort of all in one package. What if I do 2? 2 on the other side? Okay, let's see. Two. Okay. And 3? Same thing? Right here without sliding. Okay. Awesome. 4? And we're pushing to 4. So momentum is conserved. What if I go like this? It's gonna blow up. Let's see what happens. All right, ready? Pretty violent. Okay. Seeing that it does that, let's do 2. So in this system, momentum is conserved. However much velocity I give it, however much momentum I give it, will remain in the system. Okay, we're going to start this next time. Yeah.
What if you do 1 on one side, 2 on the other?
1 on one side, 2 on the other. Do it again. Ready. Alright. So I'll see you guys later. If you want to come down and play with this, you can. Right.